And then I have this background I can give you. Note that the background I'm sending you right now is for chairs. But I think it should work. It's the same background. It just says chair.
I think for the speakers, it says speaker.
Yeah. So maybe we can ask Vanessa to share her background with the rest of the.
Yeah, I try. Just a moment.
Yeah, sure. No, please also switch to the new background that Vanessa is going to share.
I'm sorry, I didn't hear that. I'm not sure.
So Vanessa is going to share a background in the chat. It's for the speakers, and you can use that specific background, the virtual background you have. You can switch to Vanessa's share.
You mean I should switch my background?
Yep.
Nana,
Yeah,
you are
it's
right.
in the chat.
Nana, you are right. Yeah, that's my background. I do not have a webcam, so I.
Okay, I sent the
maybe
file in the chat.
Yes.
And if you go quickly to the chat window, okay, frame it is rotating. That's cool. Shall we get started? Okay, hi everyone. Welcome to the rendering and display session. Today we will be hosting 5 very exciting works, 5 very exciting presentations. It covers a wide range of grounds from holography to rendering and head-mounted displays and projection and painting. These are really interesting trending topics in the field. And ISMAR is a unique place to present such work, and we are in a unique session right now. So I can speak briefly about the organization of this presentation, of this session. We will be having 5 separate presentations. Before each presentation, I will go ahead and introduce the speaker, and the presenter will present the work. Right after that, we will go into a question and ask session for each presentation. Make sure to ask your questions through Discord. There's a dedicated Discord channel. It's called Paper Session 4 Rendering and Display. You will find sub-channels in that Discord channel, and you should be able to ask your question by using these sub-channels. With that, I would like to start with the first talk of this session. The paper is titled as Agentress, Real-Time Clothing Synthesis for Virtual Agents Using Plausible Deformations. And the speaker is Nanan Wu. Nanan Wu received his PhD degree from the College of Computer Science and Technology at Zhejiang University in September 2020. His research interests include clothing, animation, and virtual reality. With that, Nanan, the floor is yours. You can go ahead and share your screen.
Well, what shall I do? Can you see my screen?
Oh, no, not really. Let me see. Do you have this option at the bottom of your interface? It's called share screen. When you move your mouse, it should appear automatically.
It's others are sharing. I cannot share the screen.
Khan, maybe you should stop sharing first.
I don't think I'm sharing. This is the share from
No, there is
Enrico.
Oh, okay. Somebody else is sharing.
So maybe we can consult with Enrico. Hi, Enrico. Can you please help us with the situation? Obviously, Nanan is not able to share.
Nana, do you hear me?
Yes.
Share option, share screen.
Yes,
The bottom.
Okay, I find it.
Okay, sounds good. Hopefully we can now start.
Can you see me?
Yes,
Yes.
yes, we can see you.
Oh, yeah, good.
Floor is yours.
Okay, I'm a little uncomfortable with my throat, so could I just play the video I recorded?
Sure, please go ahead.
Oh, yes, thank you.
So if there is a sound audio in the video, I don't think we are
Yes.
hearing it.
There is sound, but I don't know why there's no sound.
I think screen share does only share the screen, not the sound, but I'm not sure. So
Okay,
Enrico,
you mean
Enrico, can you please help us with this? We have a support here. We would like to share the video that Nanan has. Hello,
the
Enrico.
video? I cannot share the sound of the video.
Yes, what is the problem? Sorry.
The problem is Nanan is willing to share his presentation. It's a video and it has audio. Of course, when he shares the video, we can see the visuals, but not the audio. Can you please help with us?
When he shares the video, he has to put also the audio from the settings.
I'm sorry, I don't follow that.
One moment, please. When you share the screen, Zoom will say to share also the audio. Tick the box with the audio sharing, please.
Audio sharing.
Exit from screen sharing now, please.
Okay, 停止吧.
Reshare again and tick the audio box.
Okay, I'll find it. I'll find it.
Thank you.
Yes. Can you hear the voice? We proposed a real-time clothing synthesis algorithm for virtual agents using plausible deformations. Our method belongs to example-based clothing synthesis techniques. Using only a CPU, our method can generate real-time clothing animation results with detailed wrinkles for various body poses and shapes without resizing the clothes model. Our method can also be applied in VR scenarios. For a men's long-sleeved shirt with 12.2 silent vertices and 23.4 silent triangles, our method can generate realistic clothing animation for various body shapes and poses on the commodity CPU, 56 frames per second. Generally speaking, our method consists of two stages: the offline example database construction stage and the online clothing synthesis stage. In the online stage, we first use a clothing pose model to predict the clothing deformation for the query body pose and the template body shape. We refer to this as the pose dimension. Then, we compute the LBS synthesis for new body shape and original body shape with the example database. We refer to this as the shape dimension. After that, we combine the pose dimension and the shape dimension through tail expansion to get the intermediate result. Finally, we resolve the interpenetrations between the clothing mesh and the body mesh and add some decaying effects to the animation. To make our database more compact, we partition the body model into 7 regions. To calculate the LBS synthesis for each region, we find several nearby examples. For each nearby example, we first change its shape to the query shape. Then, we deform the clothing mesh towards the query pose using linear blend skinning. This process will also be done for other nearby examples. We blend the results of nearby examples to get the result of a region, and combine results of all regions to get the final LBS synthesis result. The LBS synthesis for new shape and the LBS synthesis for original shape are referred to as the shape dimension. The clothing deformation predicted by the clothing pose model is referred to as the pose dimension. Generally speaking, the tele-expansion used in our method combines these two to get the clothing deformation for the input body pose and shape. Specifically, we represent the input body with shape parameters beta and pose parameter theta. The clothing deformation can be formulated as a high-dimensional function f beta theta and approximated by the clothing on its nearby example f beta theta 0, beta 0 theta 0, using its first-order tele-expansion. We use forward difference to calculate the partial derivative. To improve the approximation accuracy, we apply the linear blend skinning method to predict the cloth deformation for the new pose from the cloth mesh on its nearby sample pose. At runtime, given a query pose and shape, we blend the tele-expansion results of nearby examples through a sensitive-based distance mirror. To generate our example database, we first select 32 motion sequences from the CMU motion capture library and sample a pose for every 4 frames. In total, we obtain 17 current different poses representing the whole pose space. Then we use k-means to classify these poses into a certain number of clusters, which will be used to generate our example database. For each cluster center, we first simulate clothing for 70 different body shapes. Then we perform principal component analysis on this clothing deformation to compute a low-dimensional subspace. After that, we learn a linear model to map the body shape parameter beta to the clothing shape coefficients. This model predicts the clothing deformation for various body shapes under a fixed body pose. We compare our clothing shape model with that of drip. We can see that our method is more accurate in terms of the average Euclidean vertex distance between the simulation result and the predicted result. Our sampling scheme can be directly used by SOR. We can see that results of SOR becomes more natural after using our sampling scheme. We apply convergence experiment to determine the number of points to use. For a men's long-sleeved shirt, our method converges after 100 data points. Results for more clothing types. Women's t-shirt with 12.0 current vertices and 23.8 current triangles, 55 frames per second. A pair of pens with 11.7 silent vertices and 22.4 silent triangles, 71 frames per second. We applied our method in 3 immersive VR scenarios. We have conducted a user study to demonstrate the perceptual benefit of our method compared to the linear blind scanning technique in generating clothing deformations for the agent in immersive settings. The user study was conducted in immersive VR scenario with an HTC Vive headset. We recorded the results of each method from a fixed angle and presented them side by side. The first scenario was comprised of a man sweeping in the living room while wearing a long-sleeved shirt and pants. The second scenario consisted of a man that has a different body shape and wiping the windows while wearing the same clothes as the first scenario. The last scenario corresponded to a woman wandering in a living room while wearing a t-shirt and shorts. Our method was taken by 18 participants, 9 males, with a mean age of 24.44 years. The standard deviation is 1.95 years. Participants can walk around and observe the agent. They were asked to indicate their preference for a method using a 7-point Likert scale. We normalized the participant responses so that 1 indicates a strong preference for our method. The participant responses clearly demonstrate the benefits of our algorithm. To summarize, our paper has 3 main contributions: a clothing shape model that efficiently and accurately predicts clothing deformations for various body shapes, tele-expression scheme to generate real-time clothing animation, and a sampling scheme that is able to find typical poses in real life. Thank you.
Thank you, Nandan, for the interesting presentation. We are now in the question and discussion session of the first paper. You can either ask your questions through Zoom chat or the Discord channel. I will be monitoring both of them. Are there any questions from the audience? Maybe I can just go ahead and start with the first question, Nandan. I'm interested in what did we learn related to virtual reality with these type of subjective experimentation. Can you elaborate on your outcomes of your virtual reality experiment?
I'm sorry, could you say your question again?
I believe you conducted a virtual reality experimentation for your algorithm.
Yes.
And if I understand correctly, it provides a more realistic view when you test this against subjects. And can you elaborate a little bit more about the outcomes? Like, where can this type of animations take the virtual reality? Like, what kind of improvement should we expect in the future?
Oh, yes. I think virtual agents, if we want to improve the perceptual, the realistic of virtual agents, we should dress them more realistic clothing animation. So, but due to the limitation of CPU or GPU, many cannot do real-time clothing animation. I believe our method can add some improve the perception of the virtual agents, and I think in the future, virtual agents will have realistic clothing animation if we want to immersive virtual reality experience.
I see. So the virtual agents can be improved this way. This is really cool. Let me see if we have another question in the chat. So let me ask you a second question then. I don't see any questions in the chat. The second question I want to ask about the data set that you use. In the data set, you show that you render multiple different poses. And then you capture these poses and use these images as your data set. Either your examples weren't showing that, or maybe it's always on the same body template. Was this the case? Were you always using the same body template? If so, would that influence the generalization of your solution?
We currently apply a simple model as our body model, and the poses are from CMU motion capture library. I believe our method can apply to other body template.
Okay.
Yes.
Thank you. I know that there is one more question. I have to skip this for the sake of time. Thank you, Nandan, for your presentation. We are going to move on to the next presenter, Jingyu Liu. And her paper is titled as Perception-Driven Hybrid Foveated Depth of Field Rendering for Head-Mounted Displays. She'll be sharing her screen in a second. While she's doing that, I will also introduce her. She's a PhD student in the Department of Photonics Engineering at the Technical University of Denmark. Her research interests include virtual reality, augmented reality, and perception-driven rendering. With that, you can take it away, Jingyu.
Thank you. Can you hear me?
Yes, I can. I think the
Great.
sound is a little bit low. Maybe you can speak to the microphone in it.
Okay, I can try to speak louder.
Yeah, this works, I think. Yeah, thanks.
Okay. So how can I take over the screen sharing?
I believe Nandan has to first stop screen share.
Oh, I can't find the button.
It's at the bottom, at the very same location where you start the screen share.
On the button, you can move your mouse to the bottom of the Zoom interface. Then the share screen will appear.
Okay. Okay, thank you, Nandan. Jingyu, can you start sharing now?
Okay. I think I'm on my slides. Can you see it?
Yes, I can. We see the
great.
PowerPoint.
Okay, yes, that should be the case.
Okay, sounds good.
I will just start.
Sure.
Hello, everyone. My name's Jingyu. Today, I will present our work, perception-driven hybrid foveated depth of field rendering for head-mount displays. Our work is featured from taking advantage of characteristics of human vision. A little bit about us. We are a team from Technical University of Denmark, Department of Photonics. And so let's start with diving into human visual model. Optical system of human eyes is far from perfection. limitation, and characteristics can form a human visual model. And the first feature I choose is visual acuity eccentricity. The eccentricity happens in both spatial resolution and color sensitivity. And the second characteristic is depth of field, which is an effect driven from divergence and accommodation. Only the objects in focus will appear sharp on retina. And the last one is longitudinal chromatic aberration. The eye's optical elements have different refractive index for different wavelengths. Short wavelengths, for example, blue, are refractive more than the long ones. So that's 3 features I select. So next, we will go through some features of head-mount displays. A mid-end resolution head-mount display has the same level of megapixel computation workload as a high-resolution desktop display. And not to mention that the next generations of head-mount displays will keep rising this computation workload. And the VR headset has a very large field of view. According to a research from 2017, only 4% of the pixels fall in the foveated region on retina. And this number is much lower than other forms of displays, which brings in a huge potential for optimization. And next, we will start with some representative method in the literature. And we start with foveated rendering. A typical implementation for foveated rendering is to divide screen into different regions and render each region with its unique resolution. However, this type of implementation is not coherent with how we perceive pixels on the screen. And later, there's a work from Stengel et al. Applies gradually changed resolution. However, that methodology is very expensive for the GPU. And to make the computation more GPU friendly, another work from Mon et al. Realized the scaling through coordinate translation. However, the sample number is too concentrated towards the central area, even though you can toggle distribution function, distribution through the kernel function. And a newer literature applies a human visual model-based sampling distribution together with the coordinate transformation. And this human visual model-based distribution is also the one that we adapt in our method. Note the original implementation is with path tracing, which is challenging for complex things. And next, we will look at depth of field rendering method associated with foveated rendering. Commonly, depth of field is realized through post-processing, and a point will appear as a circle due to the out-of-focus blur effect from lenses. A work from Ware et al. Is a good example for applying depth of field on top of foveated rendering. However, this work doesn't account for human vision parameters. Also, post-processing is an extra step and will slow down the performance. And another work from Tucson et al. Realized content-based foveated rendering, which at the same time realized depth of field to a certain degree. However, the depth of field simulation is not physically correct in this approach. And last is about longitudinal chromatic aberration. An example is from Holographic et al. LCA is happening along with depth of field, since this phenomenon only appears in out-of-focus regions. However, this specific work doesn't include foveation. So with all these background stories, we will introduce the method proposed. Our hybrid rendering is featured from a two-step judgment, in foveated and in focus. Only the pixel or object fulfill both of the judgment will be rendered out in a full resolution. And this composite scaling strategy makes the depth of field sampling actually contribute to the performance comparing with the literature. And as for the sampling strategy we applied for foveation, we adapt retinal Galilean cell distribution function in the literature. And the scaling is through coordinate transformation, and we do an inversion sampling on cumulative distribution function, where alpha is the eccentricity angle, and the CDF integrates over 0 to the maximum of field of view. As for the depth of field sampling, we apply the sampling on top of a thin length depth of field boundary function set. And we made an adaptation towards human visual model and head mount displays. For example, we adapt pupil size from eye tracker, as well as the low luminance level in a VR headset. And this data is from literature. So this are taken into consideration as parameters for the model. As for the autofocus blur, we applied bulk blur, which at the same time realize anti-aliasing. And this physically correct approach is better than the traditional anti-aliasing method that applies Gaussian filter, for example. The circle of confusion size is parameterized with human vision parameter. And this integrated manner for anti-aliasing doesn't bring in extra cost in addition to autofocus blur. And to summarize our pipeline, we first do a coordinate transformation for foveation sampling. And then we apply a Russian roulette for depth of field sampling. So this Russian roulette is realized through weighting function according to the depth of field distribution. And these two combine as the scaling path. Later, we do a inversion transformation from polar space to Cartesian space. And finally, we do a post-processing for realizing autofocus bulk blur. And some other features, including longitudinal chromatic aberration. For this one, if the pixel is further away than the furthest boundary, then the top two rows of the bulk kernel will fill out blue, and the bottom two rows will fill out red, and it's the other way around if the pixel is in the nearer field. And because our longitude chromatic aberration module is integrated with the bulk kernel, it doesn't bring in extra performance cost. Color vision for perception-driven rendering is a relative new field. We did a preliminary test and invite some subjects to observe their interaction with this feature. And we noticed most subjects won't tell the difference from if we toggle the module on and off. It's something that was further investment with a full subjective test. And as for geometry simplification in the peripheral area, this will reduce a large number of triangles in the peripheral area. We also did a preliminary test on this feature. And we noticed that most subjects is very tolerant towards geometry modeling, even when it happens on the occlusion boundaries. So they will not feel uncomfortable for this feature. And we did experiment on our method. Here is some example for the result. The foveated and in focus region is with brown square, and the other pixels are marked with gray square. And we also set up a comparison experiment with the literature. We compared our method with Mon et al. For fair comparison, we set a preset camera path and a gaze trajectory pre-record one. And the simulation is done on a desktop display. As for the result, here is the frame rate or performance for the simulation on the desktop display. And as you can see, our method achieves better performance across all the test scenes. And as for the perceptual quality, we used a perceptual-based matrix called for video VDP, which can handle large field of view displays such as VR headset. And as you can see, we achieve better performance 4 out of 6 test scenes in total, and we have a better standard deviation. To summary, we bring in a model that emulates human eyes depth of field in VR. And our hybrid rendering method can realize retina blur with a composite scaling strategy. And we extend the scope of human visual model by accounting for longitude chromatic aberration with block blur. As for the future work, we would like to verify whether hybrid rendering can relieve versions accommodation conflict as a pure software solution, and how users' attention interact with perception-driven rendering methods. And we also would like to do an application study to model the relationship of perceptual quality and performance for every separate features of our model. So I think that's it for my presentation. I'm open for questions. Thanks for your attention.
Thank you, Jingyu, for the nice presentation. I think the foveated rendering as a whole topic has been on the rise, and I can see multiple papers in the last years, basically. So we can now take questions for the second paper. For the newcomers, I repeat, you can either use Discord or this Zoom sessions chat window to ask your questions. If there aren't any other question, as far as I can see, there's no questions yet in the chat. Let me go ahead and start with the first question, Jingyu. It's often the case the foveated rendering pipelines require, hacking things and getting it run, and it's always against, somehow the way the graphics pipelines are, currently designed, right? So the computational benefits that it is promising is always hard to show. Can you elaborate a little bit more on that front? Like, what do you think is the roadblock in this case? What is the thing that is stopping us getting these benefits?
I think one thing you mentioned is about the computation efficiency in the architecture side. So as far as I learned, currently, such as NVIDIA and also Adobe, those, especially NVIDIA, it's providing its own, it's not only target for foveated rendering, but for multi-resolution or multi-scaling method. So I can see that they already start to support this very scaling rendering strategy in their architectural level. And although as far as I learned, this implementation on the low level is more straightforward, as one of the slides I showed before, which is more like simply dividing the screen into multiple regions and render it out for different resolution. It's not necessarily taking account for a real human visual model inside. However, it's already a trend that these manufacturers and the GPU architecture itself start to adapt this trend for foveated rendering or other how to say implementation that maybe can utilize the similar strategy or mechanism, but not only targeting for this like foveation in the rendering. That would be my my thinking towards this trend.
I see. So you're saying that the multi-resolution approach that these companies are supporting nowadays is helpful
I can see it's
to
now the trend.
push this field forward.
Yes.
Can you also elaborate a little bit more about your technique and how applicable is it to this trend of multi-resolution? What is the compute overhead? Like, can you give us some ideas along those lines?
So for my methodology, it's not directly coherent with the GPU architecture because for their API, at least as far as I found, it doesn't include any like coordinate transformation. It's just like divide the screen in the Cartesian space. For utilizing my method on those low level implementations, we need to do some modification on the method. So basically, we need to take the coordinate transformation part and only utilizing the model, so which is the background for the distribution, the human vision model, and then do a direct implementation on the like multi-resolution rendering that their platform support. However, the logic and the backend distribution can still be maintained and applied. So the method is not, I would say the method is not directly applicable on the low level API that those GPU companies provide, but it can be easily translated to those tools that can be directly utilized for now.
Okay, I understand that there is hope for foveated rendering. And thank you for your nice presentation and thank you for answering our questions, Jingyu. I will now move on to the next presenter. Please stop your screen share.
Sure.
Our next paper is long-range augmented reality with dynamic occlusion rendering. And the presenter is Mikhail Zizinstev, if I'm pronouncing correctly. That's his surname. Hopefully it's correct.
Zizinstev, but it's close enough.
Okay,
yeah.
Sorry for this.
Okay, so
he's a research scientist in the Center of Vision Technologies at SRI International, Princeton in the States. His research interests include multi-sensory navigation, stereo, motion processing, and augmented reality. With that, you can take it away, Mikhail.
yes, so I assume you can see my screen share and can hear me well, right?
Not really. I cannot see your screen share, to be honest.
Oh, you can't?
Yeah.
Okay. Just a moment. How about now?
Yes. Now we can see.
Now we can. Okay, good.
Sounds cool.
All right. Just a moment. Okay, so hi. Allow me to introduce our work called long-range augmented reality with dynamic occlusion rendering. So my name is Mikhail Sizintsev, and this is our full team consisting of Nilotopol, Han Chu, Supun Samarasekar, and Rakesh Kumar. We all from SRI International in Princeton, New Jersey, USA. And this work was part of the large-scale project funded by Office of Naval Research from US government. So the overall problem we are addressing is augmented reality with occlusions. It is well known that occlusions are important for proper AR experience. And in this example, we want to insert virtual excavators in front of the cars and also the excavator behind the row of real cars. And to do it correctly, the Close excavator must occlude cars, while the cars themselves should occlude the further excavator. Occlusions by synthetic avatar is trivial, but occlusions by real objects is not, that are not in the scene is much harder, because you essentially need to know the occlusion mask of these corresponding real objects. And for that, one would require accurate depth measurements and accurate 3D boundary outlines. So the problem of occlusion reasoning has been addressed before, including our lab. And there are a number of existing systems that can effectively deal with occlusions at close range, and especially in so-called room scale AR. The major reason for success is availability of good quality real-time depth inference technologies, such as stereo, structured light, and flash lidars. Also, most of the techniques can create 3D models of the world on the fly and interact with them later. But the situation is much harder when we deal with a long-range geolocated AR. Specifically, outdoor and in open space where insertions can be placed hundreds of meters away. And the main problem is that it's much harder to obtain reliable depth estimates. For example, stereo has too narrow baseline, and error becomes too high. Moreover, we currently seek solutions that do not use any form of long-range lidars, because lidars are still bulky for head-worn systems, which we're aiming for. They're expensive, power-hungry, and still provide mostly sparse measurements. Even though it was hard to measure depth accuracy directly, we can use semantic reasoning to infer depth of certain object classes, such as cars. And with the help of base scene 3D model, we can infer their depth. So for example, we can detect the cars, get the depth from the ground plane, and then use them for proper occlusion reasoning. So let's see how it is actually done. First of all, this exact idea was first proposed by us in the paper published in Virtual Reality Conference back in 2018. And while we presented a method for depth inference and occlusion reasoning, the pipeline had this so-called linear execution flow and was mostly suitable for offline processing and video see-through systems. Specifically, all the input data was first processed by the navigation module, and then objects were detected and depth was inferred for them. But the main problem with such organization is the depth inference is slow. It's a slow module and involves executing a high memory footprint neural network and also additional 3D render. It creates high latency and challenging to run in real time, especially on small, lower power mobile hardware. In the proposed work, our first contribution is to significantly modify the AR pipeline itself. Specifically, we organize navigation and depth inference modules to run in parallel, and also introduce this additional dynamic object tracking module. This model warps the occlusion and depth maps toward the latest AR frame and effectively hides the high latency of this depth inference module. So let's go into details of each of the modules. So first, the navigation block, and this paper is not concerned with pose estimation per se in any way, so we just borrow from our previous technology of geolocated AR. All of the components of our outdoor AR system were presented previously at this SMART conferences a while back. And in short, this is a visual inertial tracking technology that fuses measurements from different sensors. IMU, stereo, mono cameras, GPS, magnetometer. We can use our prototype sensor head, as depicted here, which contains all sensors mounted on a helmet, or use off-the-shelf commercial hardware like Intel RealSense, which also has a synchronized IMU and camera streams. The tracking algorithm itself is based on error state Kalman filter and exhibit good performance and low error rates that are very similar to the algorithms of the same class. It also has quite low global positional and orientation errors. So the next module is the depth inference module, and it consists of two major steps. So the first step involves finding object of interest in image to be augmented. And this object of interest include cars, pedestrians, bicycles, animals, or anything else that are not part of the terrain of buildings. So for object delineation, we rely on the off-the-shelf instant segmentation methods like Maskar CNN or YOLO. And our current system uses YOLACT, as it is quite fast while providing fairly good quality object boundaries. And but it can also be replaced by more recent advances in this area. So the second step of depth inference is so-called depth from terrain, and it works as follows. So first of all, we must have some model of a terrain in order to place our AR insertions. And this model can be a simple digital elevation model of them, scans from aerial lidars, or even 3D reconstruction obtained from a flying drone. For every input frame in the navigation module will produce us the pose. And this pose is used to render terrain from the sample viewpoint. So if we overlay the rendering of the frame and get the depth, we can get the depth proxy for the large structures and the terrain itself. So now the task becomes how to figure out the depth of segmented objects like cars that are not in the 3D model. And what we do is we assume that those objects reside on the ground, and the lowest point along the gravity vector, which intersects the ground plane, will define the depth for the whole object. So finally, it is important to remind that the whole depth inference module is computationally involved. You need a network to run instant segmentation, and you need a separate renderer to produce the terrain maps. That's why we have this dynamic object tracking module that is meant to work in conjunction with the depth inference module. And the purpose of this module is that given the depth and occlusion map for previous frame T0, quickly warp them to the future frame T1. And since this step must be done as fast as possible, we are treating each occlusion mask as a template and track it between two images using a fine model constraint. So for tracking, any fast method can be used, and we rely on modifications of Lucas-Canadi algorithm with Laplacian pyramids. So another extension of this template tracking is that we can reuse the inferred affine model motion parameters and extrapolate or predict the displacement of template even to the further time T2. So this will effectively allow to warp us occlusion map in future and make it available for optical see-through rendering. So after talking about system components, let's look at some results. So here is some short clips of sequence of a person moving through the field with many static and some moving objects. Synthetic excavators are being inserted in the few spots and are properly occluded by real cars. These are a couple of representative frames where cars are partially occluded by the cars partially occlude excavators behind them. And in this frame, we even managed to track a moving bicycle in front of the excavator. So, one more example. All right, so here is another representative example. And this time the observer is mostly in one spot, but the cars and trucks are moving on the road. Again, if we pause in certain spots, we can see the cars and trucks properly occlude the excavator on the other side of the road, while the closer excavator will always occlude the cars which actually in front of the road. Also, I want to stress that dynamic object tracking module is very important for this kind of sequence to work in real time. All right. So, of course, the proposed method has a number of limitations. First of all, we are dependent a lot on the quality of instance segmentation. Specifically, our occlusion masks better have good 3D boundaries, and we do not want to have any missed object detections. Next, in order to keep the object tracking module efficient, we have to rely on the affine constraint, which is quite problematic for fast-moving, non-rigid and deformable objects. And finally, the method assumes the observability of a point of intersection between the object and the terrain. And this is our depth, main depth measurement. Meanwhile, this point can simply not be visible if the lower part of the object is occluded by another object or terrain itself, like a small hill. And finally, some objects simply do not reside on the terrain. It could be like a flying drone. This obvious idea is to switch to depth from single image technique, and the option is investigated on our paper in greater detail. And another important aspect I want to mention is the expected error of this so-called depth from terrain method. So without loss of generality, we can consider a camera looking at some planar terrain And it is not hard to derive the depth. Error depends on the distance of the terrain intersection point and some other parameters like camera height and focal length. So in fact, this method is just another depth from triangulation technique and has error behavior similar to stereo. It grows quadratically with measured distance, and camera height essentially acts as a baseline, which is normally within 1 or 2 meters, and it is much better than any stereo. Thus, if you want to increase depth precision, we either increase height by going to high grounds, or we increase the focal length and use telescoping systems. So in conclusion, we presented a practical method for AR insertion at long ranges without explicit depth sensing. The proposed architecture allows to perform AR with occlusions in real time and run pipeline even on smaller and lower power hardware. And regarding the method itself, candidate occluders are extracted by semantic instant segmentation, and their method depth is inferred from terrain and model viewpoint. We also introduce additional tracking module that effectively effectively adjusts masks to latest AR images and poses and allow for optical and video see-through renderings. And that will be all, and I'm ready to take questions. Thank you.
Thank you, Michael, for the nice presentation. We are now in the question and answer session for the paper 3. You can either ask your question using the Discord channel or the Zoom chat. Are there any questions from the audience? Maybe I can go ahead and start with the first question. So I believe, if I'm understanding you correctly, Mikhail, you're approaching this problem of occlusion in the military applications, right? Some of the examples you have given from the past, they were military applications, if I understand correctly.
That's correct, yeah.
So in that respect, if you look into the consumer level devices, people are trying to move away from the cameras. A good example is from Facebook, for example. They have recently released some product with some company called Ray-Ban, which all of us know perfectly, of course. So can you elaborate a little bit more about the path these people are taking? Like they are miniaturizing their cameras, they are less dependent on their cameras. There are even some people speaking about removing cameras completely and going into the gyroscope based location finding opportunities. But I mean, this poses a challenge obviously for occlusion because you don't know the scene, the world environment around you anymore. So can you elaborate a little bit more about that? Like, do you think cameras are here to stay in augmented reality devices, or they are most needed, or do you think there might be a way to fix these issues that you're showing right now in the future with the paths that these other companies are taking?
Yeah, I guess the use of camera is like the bottom of it goes to this cost-benefit analysis. So main reason we use camera currently in optical see-through systems, right? Because for video see-through, you need the camera. That's your background. But in optical see-through, it's just a part of the tracking technology. And it's been traditionally all right now that visual inertial tracking is one of the most robust thing which runs on low power hardware, and so actually pretty cheap as well. So that's part of the reason why we still have it. And even frankly speaking, right now, most of the cameras, they're still black and white or very fisheye lens. So getting the depth from them is actually not direct. It's actually hard. So for example, you don't have a color, segmentation would be harder and things like that. I actually think, and that's a question I got a lot when I'm showing this presentation to people, that they all know about other sensing technologies like even LiDARs. LiDARs are still getting smaller, they're getting cheaper, they're getting denser. And essentially, if you have a LiDAR which really senses everything at a high rate, you might get away without using it. But the truth is, I guess it's all when do you want to use this technology? If you want to wait another 10, 20 years, maybe yes, indeed. And even that is not guaranteed. But the thing is right now that whenever we want to deploy it on a person, especially, not on a car somewhere, you have to put everything on your head. And it should be relatively light, so it won't break your neck when you turn your head around. So I guess this kind of combination provides you something which still gives you a good perceptive quality. So that's my take. So I guess even if the camera, you can still keep the camera even for like inferring occlusions, and it shouldn't really give you make it more expensive or make it harder for the whole system. But again, it's provided that there is nothing else.
Yeah. So you say, if I understand you correctly, you say lidars might be one option in the future, and but it requires further research, and maybe we need to wait like 10 more years or 20 more years.
Yeah, I think the
that
LiDAR itself, it might be a bit harder from engineering perspective to make it of the same power footprint and the same size footprint. Those LiDARs, they're also, there is a question of density. Actually, if you can, most of the good depth inference methods right now, they use LiDAR in combination with the RGB image, right? Especially for the farther distances. So images really help a lot because like just from simple geometry, the farther you sample the points, the more distance in between the samples. And there, so you're still kind of dealing with the same problem, I would say, yeah.
Maybe I can extend my question a little bit.
Sure.
There is this recent trend of event cameras, which proposes to decrease the data bandwidth and only give you the differences between images. Basically, it's like I would call it like a differentiable camera of some sort.
Yeah.
So do you think that kind of devices might be important in the future for such development?
For the development of occlusion?
Yeah.
No, I think you can definitely use it because eventually, if you like integrated information from the camera, you can reconstruct the image itself. Although the purpose of them is not to get the image. The purpose of them is actually even the people right now, they use them for tracking, but they don't try to reconstruct the image. They actually can track the features in much higher frame rate. So right now, I would say it would be harder to apply them directly in here. But at the same time, it would be, it's actually should give us a great benefit in order to get a very fast rate updates to the depths, maps themselves. For example, if you move a lot or if the objects move a lot. So maybe if you're able to initialize it properly, I kind of don't, on the top of my head, I cannot see how it is easy to initialize. Maybe you have some other camera to start with. But in order to update depth frames, it would be actually very beneficial to use event cameras, I would say, yeah.
Thank you, Michael, for the nice presentation and answering my questions. I will now move on to the next presenter. So our next paper is paper 4, Scan and Paint, Image-Based Projection Painting. And our presenter is Vanessa Klein. And let me introduce Vanessa to you. And Vanessa has received her BS and MS degrees from Friedrich Alexander University, Erlangen-Nuremberg, in the Department of Computer Science. She is currently a PhD student, and her research interest includes spatial augmented reality and projector camera systems. With that, floor is yours, Vanessa.
Yes, thank you for the introduction. So, in the past, our lab has worked intensively with different kinds of projection mapping systems and applications. One of our main goals is to make projection painting easily accessible to anyone. With projection painting, you paint with a digital brush, but in the real world. For example, white statues can be painted to look like they still have their original colors. And since it's only projected light, projection painting doesn't damage the material, and you have all the other benefits from digital applications like saving your art or undoing a mistake. So accessible projection painting requires an automatic camera and projector calibration, a projection mapping core algorithm that optimizes the pixel luminance across multiple projectors, and an easy-to-use projection painting application. The basic hardware setup includes a projector, the target object to project on, and a depth camera to track the object's position and orientation. And additionally, we require a high-quality mesh of the target object. The mesh is important not only for rendering the actual content, but also to compute the luminance for each projector pixel to achieve a convincing and realistic result. And while the setup is not very expensive and our applications already target non-experts, it's this high quality scan that currently limits projection painting to users with experience in 3D scanning. And of course, you need the time to perform a high quality 3D scan beforehand. And as trivial as it might sound to experts, 3D scanning for projection painting requires quite some preparations. First, you need to know exactly which object you want to scan. Then you have to bring your equipment and perform the actual scanning, which also takes some time. And if you want to be able to store colors with the reconstructed mesh, you must generate a fitting UV map. But what if there's no time for preparations? What if you're a designer and have to sketch a design on a new prototype in a spontaneous meeting? So we asked ourselves, can we do without a mesh? Can we perform projection painting on unknown objects? The setup already contains a camera and projector. Can we use these to 3D scan the object on the fly and only when needed? And to store the painted color, can we replace the necessary UV map with an image-based rendering approach? So to answer these questions, we revisited our projection mapping core algorithm that determines the luminance for each projector pixel. The algorithm does not require a mesh per se. Instead, it requires per projector pixel the target object depth and the desired paint color. And for the depth data, unfortunately, we cannot rely on the depth camera since the depth images are too noisy. But for a single projector view, it is simple to perform a structured light scan for high quality depth data. But as soon as the object or the setup is moved, the projector's view doesn't match the depth data anymore. So we need multiple scans to cover the projection surface. In that case, a single scan should be fast and still provide the high quality depth data. We therefore implemented the Chebyshev phase shifting algorithm by Moreno et al. The grayscale variant of the algorithm requires only 3 shifted images of 3 different sinusoidal pattern frequencies. So a single scan is fast, but scanning still interrupts the painting session of the user. And that's why new scans should be performed only rarely. And we have to remember that for our problem, we don't need a mesh. We only need a depth map for the projector's view. So whenever possible, the existing recorded depth maps are fused in screen space to create a new synthetic depth map for the projector, like an image-based rendering. And for this task, we employ fragment fusion by Rückert et al. Fragment fusion basically replaces depth testing during rendering with averaging the values at the same pixel. Values that lie in the background are discarded, but values that describe the same surface are averaged based on their angle between the recording keyframe and the rendering camera. And values in the foreground replace the current estimate. So all in all, given that we already have some recorded depth maps, we can easily generate a new synthetic view from them. But when should we record a new depth map? New scans are necessary only if the object is moved, for example, rotated. And the user the less the user is interrupted by scans, the better. A first scan is always performed upon startup. And from then on, we track the object via the depth stream of the camera. The user determines a rotation threshold for their object, for example, 45 degrees. And if the object is then rotated by 45 degrees, the rotation trigger fires and a new structured light scan is performed. If the trigger, the trigger always considers the closest already existing scan view for performing the threshold check. And if we continue to rotate the object, but in the other direction now, no new scan is triggered until 45 degrees are reached again towards the closest scan view, which in this case is P1. So we can rotate the object a full 90 degrees before a new scan is triggered. And if we change the direction again, this time it takes even longer, 135 degrees before a new scan is triggered, since the closest scan is first P3, then P1 and P2 afterwards. And after the object has been moved by 315 degrees in total, the rotation trigger won't fire anymore, since there's always a scan view closer than 45 degrees. Another way of moving an object, of course, is translation. And to track how far the object is moved, we follow the center of gravity of the closest existing scan. But we don't use this distance directly, because if we did, the user would always have to move the object the same distance. regardless if the first scan is already large, like here on the left, and is easily trackable and offers a lot of surface to paint on, or if the first scan is rather small, like on the right here, is therefore hard to track. There is not a lot of surface that can be painted. Yeah. So to take the scan's dimensions into account, we determine the scan's capture area. The capture area is an estimate of the target object's dimensions. It's a box that is centered around the center of gravity and stretches towards the closest camera frame border. And to trigger a new structured light scan, the translation trigger considers now the ratio of D to S and fires if it exceeds a threshold. And by relying on this ratio, we achieve an approximately constant surface gain with each scan. A large scan is tracked for a longer distance until a new scan is started, and a small scan is tracked for a shorter distance. Compared to a regular bounding box, the capture area may also include some empty space, for example, if a small object is fully visible in the camera frame. And that way, the empty space contributes to the scan, and small objects are artificially enlarged for the trigger, and this reduces the number of unnecessary scans when moving the object. The rotation and translation trigger already cover a lot of situations when a new scan is necessary, but they don't consider the actual shape of the object. In this example here, a rotation threshold of 45 degrees is ideal for this octagon, but the notch on the left side is a real problem. Using the existing scan views, the yellow parts can be reconstructed only poorly, and the red part not at all due to self-shadowing. So we require a third kind of scan trigger that issues a structured light scan for areas that aren't covered well enough by the rotation and translation trigger. And we call that trigger the quality trigger. So when scanning the surface, we assign each depth value a confidence value based on its recording angle and how close it is to holes and borders. And in every frame, we then render the scene from the RGB camera's perspective and use fragment fusion to fuse these confidence values into a confidence map. If the rendered frame contains too many bad quality pixels, highlighted in red here, we must assume that the quality from this perspective is insufficient, and in that case, we trigger a new scan immediately to fix the bad quality. So at this point, we are able to iteratively scan an object with an automated trigger system and use fragment fusion to render them. But we still need a way to store the painted color from the user. And since we have no full mesh, we also don't have a UV map. So to solve this problem, we think the fragment fusion algorithm backwards. Since the depth is stored in images and fused in every frame, why can't we do the same for the color? We have to save the color in a way that it can be used by fragment fusion. The user paints their view of the scene by painting into a paint texture. The texture lies in front of the scene, so it's like painting on transparent foil. The paint strokes are then reprojected into all scan views and stored in virtual camera images. So when rendering the scene each frame, the color is simply included in the fusion process. We tested our system with several objects, including everyday items like shoes. The first scan, as I said, is triggered automatically when the program starts. The patterns are projected and captured by the camera. And once the first depth map is reconstructed, the user is able to paint all scanned areas. And while the user is painting, the paint is immediately projected onto the real-world target object. And whenever needed, the user may move the object and the projection follows. And of course, if necessary, the triggers start new structured light scans to expand the depth dataset. The depth maps are aligned and the user may continue painting. Since the user rotates the victory statue in the other direction now, the statue can be moved a lot farther compared to the first rotation before the next scan starts. And for a complex model like this, with a lot of folds and self-shadowing, we required 17 scans on average to cover the whole object. We used a rotation threshold of 45 degrees for this statue, but it was mainly the quality trigger that started new scans. But a great advantage of our technique is surface that isn't needed isn't scanned. If you spontaneously decide during your painting session that you want to paint the back of the statue and not only the front, you can simply do so. In ordinary 3D scanning as a preparation step, you would either have wasted time by preparing a surface you don't need, or you skipped areas and then cannot spontaneously change your plans. So our system gives you the total freedom to be as spontaneous as you need, and all that on a completely unknown object and without preparations. Thank you.
Vanessa, thank you very much for the nice presentation. This is highly interesting and impressive.
Thank you.
So we can now take questions for the paper number 4. You can ask your questions either on the Zoom chat, or you can also use the Discord channel, which is paper 4's Discord channel, paper session 4. So let me see if there are any questions in the chat. I don't see. Okay, there's one actually. This question is from Henry Fuchs. He's asking, what happens in difficult areas like transparent visor of the helmet?
We use structured light scans. So of course, our method is only as strong as the structured light scan method that we use. So Chebyshev phase shifting is no specialty in that case. And transparent areas cannot be really scanned at all. Yeah, you have to change the reconstruction method, and you could maybe mix methods. So while the depth image from the camera is too noisy, maybe it could contribute in some cases, but of course the depth image will also have troubles to reconstruct the transparent areas. So unfortunately, I think structured light methods are not really suited for transparent areas, and best, of course, for diffuse materials.
I'm assuming that this answers the question, and I would like to ask you one more question, Vanessa, real quick. We often see these monocular depth estimation work appearing in other conferences like computer vision conferences. Yes, they don't provide the depth as detailed as in your case, but do you see this work at some point maybe relying on such methodology, or do you think this can never happen? Maybe there's a theoretical limit that bounds us not to use existing phones or cameras. Can you elaborate a little bit on that front?
I think it would be pretty interesting to try it out. We have to use very high quality depth data, otherwise the projection will always appear a bit off. But I think maybe not. Why not try it? Since we use confidence values to assess the quality of a reconstructed depth value, maybe you could fill in those values with other techniques. So I think it's a very interesting idea.
So some sort of hallucination might help to improve the data quality. Got it. So the third question is from Daisuke Iwai. He's asking, are you considering to extend this system to multi-projection?
Okay, so our current prototype does not use multi-projection, but we designed the whole system to be capable of it, because we base the core projection mapping algorithm on our prior work, and everything that we need for multi-projection to work is really only the depth map for the projector and the color. If you use multiple projectors, then for example, 2 projectors, then you need 2 depth maps, 1 for each projector, and 2 color maps, color textures, 1 for each projector again. And in that case, you simply use fragment fusion to render the projector content for 2 projectors. So we did not try it out, but to us, it's very plausible that it works with multiple projectors, since you use just 1 render pass more with fragment fusion.
I'm also guessing with the increased complexity of the system, I think you may also end up having other troubles like, mutual projections may be hard to, to understand in the first place. Maybe you need some temporal approaches, projector 1, projector 2, in a time sequential way, something like this.
Yeah, of course, you would need to scan one after another, for example, but then you have multiple scans from multiple perspectives at the same time. So there are benefits to multiple projectors.
Yeah. This is a highly interesting work, Vanessa. Thank you very much for the nice presentation and answering our questions. We will now move on to the last presentation of this session, paper 5. It's called Gaze Contingent Retinal Speckle Suppression in holographic displays. And the presenter of the work, let me introduce you Praneeth Chakravartula. He's a research fellow at Princeton University, working on next generation novel near-eye displays for virtual and augmented reality. His research interests lie at the intersection of optics and graphics. His work was awarded Emerging Technologies Best in Show Award at SIGGRAPH 2018 and Best Paper Photonics West 2020, formerly known as OSA, Optica nowadays. He also received a Biophotonics Award in 2020 and IEEE VR 2019 and ISMART 2018. He has a highly interesting background and lots of awards that he has received for his work. So Praneeth, floor is all yours. I believe you're muted.
Can you hear me?
Yes.
Yeah, thanks for the introduction. Hi, I'm Praneeth. I'm presenting a paper on gaze contingent retinal speckle suppression for perceptually matched foveated holographic displays. This is joint work with Zhan Zhang, Okan Tursun, Piotr Didek, Chi Sun, and Henry Fuchs. So we all believe that augmented reality is going to revolutionize personal computing, and this technology is gathering momentum every passing day and hour, transforming and helping us reimagine the future. But however, if you look at the headsets that are being promised today, it is not reasonable to expect that we'll wear these helmet-like devices all day, every day. And in fact, if you look at the existing displays, they have narrow field of view, they are bulky in form factor, they present modest image quality, they have no support for focal accommodation or prescription, and they roughly have approximately like 2 to 3 hours of battery life. However, for AR to be practical and widely accepted, all future displays need to be like everyday eyeglasses, presenting wide field of view, having a compact form factor, presenting high resolution and high image quality, having support for focal accommodation, 3D eye tracking, prescription support that is integrated, long battery life, onboard sensors, and so on and so forth. And we hope that we achieve all of these in the next 10 years. So over the last few years, researchers have tried different display technologies approaching really compact form factors. But of all these technologies, perhaps holographic displays is the only technology that has shown promise of getting everything that we need in an eyeglasses-like form factor. So how do holographic displays work? So an incoming light wave is typically modulated by a phase pattern on a spatial light modulator. And this modulated wave propagates to a distance and creates an interference pattern, which is our image on a holographic display. And computing the appropriate phase modulation on the spatial light modulator, that is the core challenge of computer-generated holography. And this phase pattern directly affects the quality of the holographic images on such displays. So algorithms for holographic phase retrieval has seen a significant advancement in the recent years with the introduction of Wirtinger gradient-based stochastic gradient descent optimization techniques. And specifically, since the wave propagation model is unknown within a real holographic display, recent methods try to compensate for all the real-world aberrations by optimizing for images that are directly coming out of the display and as captured by a camera. So this is like in a hardware in the loop or a camera in the loop fashion, where all the errors between the captured image and the target image are back propagated into the holograph phase. And this is done multiple times until a good phase pattern is reached. So such optimization techniques for computing phase holograms will translate to high perceptual quality images as seen by a human user or a human eye, if only the eye is similar to that of a camera. But however, depending on our pupil opening, time of the day, and other factors, our eyes can have a non-sharp PSF on the retina. And this causes mutual interference of the modulated coherent wave, causing subjective speckle noise. So although the holograms are optimized for high image quality, the mutual interference due to the PSF on the retina causes speckle noise. And unfortunately, it is not easy to just calibrate this mutual interference due to the eye PSF, as every eye produces more or less a unique PSF on the retina. So the ultimate goal of a near eye display is for these displayed images to look good to a human eye. And therefore, it is necessary to incorporate the perceptual aspects of human visual system. So if you look at the cone cells or the photoreceptors on the retina, which are responsible for color vision, they are very dense in the fovea and are progressively sparse in the periphery. And as a result, we perceive high resolution imagery in the fovea and progressively decreasing resolution in the peripheral vision. And this can be analytically described based on the ganglion cell density. So due to this, the perceived images on the eye look something like this. The fovea perceives imagery in high resolution, as you can see here, and the periphery in reduced spatial resolution. And specifically, the perceived resolution quickly drops away from the fovea. So considering these perceptual aspects of human visual system, namely the spatial acuity and the retinal PSF, we introduced a method to compute subjectively high quality holograms for a holographic near eye display. So here I show holograms computed using the state-of-the-art methods, which do not consider human perception. And as you can notice, the user will see subjective speckle noise. And on the left, you see a simulated display reconstruction. And on the right, you see the simulated retinal image. And the noise is more pronounced in the fovea because of high spatial acuity than in the periphery. And in the periphery, due to the resolution loss, you see that the noise is slightly suppressed. But however, the images are subjectively a lot noisy. However, if considering the spatial acuity and retinal PSF, here I show the holograms that are computed using our perceptually informed optimization method. And to this end, we optimize a PSF function using a large data set of human retinal PSFs and improve the perceived image quality of the hologram significantly. So because of the weighting that is based on the ganglion cell density, we have a very high resolution in the fovea, and we have some amount of noise that is still remaining in the image that are pushed to the imperceptible parts of periphery. So overall image looks of very high quality. So our optimization method generates holograms of quality that can generalize to a large variety of retinal PSFs as shown here. So here on the left, you see target image and the subjective speckle noise that is perceived with the holograms computed using existing methods. And because of our optimization, which considers a large data set of retinal PSFs, you see that the optimized holograms are of high perceptual quality for a variety of retinal PSFs, as you can see here. So basically, this means that you don't have to characterize the optimization based on an individual unique PSF. So we also conducted quantitative and subjective evaluations and validate that our method reduces the overall error compared to several existing baseline methods. Here I show the mean square error, perceptually based image quality evaluator, and the HDR VDP. And here I show the results from subjective studies where the users judged that our perceptually optimized holograms to show higher quality compared to all other baselines, like, considering no retinal PSF or considering no foveation. So I hope that I've convinced you with this that including perceptual aspects of human visual system is necessary for computing imagery for future displays, and especially for holography. And I hope that this work motivates new research in this direction. So for more details, I refer you to our paper, and thank you. I'll take questions.
Thank you very much, Pranit, for the highly exciting presentation. For me, displays are pretty important, and it's the core element of this conference, if you ask me, because virtual reality and augmented reality, if you want these things to get better, the displays have to evolve. And obviously, perception is a big argument in that front. With that, the floor is open for the question and discussion on paper number 5. If you have questions, you can either use Zoom chat or you can also use Discord channels dedicated to this paper. Yeah, let's see if there are any questions from the audience. If not, maybe I can just start by asking you a very general question about the computer-generated holography and holography in general. What is it that the computer-generated holography and holography can provide with respect to the existing methodologies like conventional imaging? What is it that they cannot do? Because we are seeing really interesting devices out there, right? And they keep on improving. What is the big promise here?
So it's a good question. Why holographic displays in the first place? So if you look at any of these existing displays, we want, we want 3D cues that needs to be presented in an existing display, and for that, so commercially available displays, they do not generate 3D cues well, because these use refractive elements where we have a display and a refractive lens that is magnifying the display. And so this increases the bulk and it limits the capabilities. Whereas with holography, you can basically snap all the bulk of optics into a single phase or a single hologram. So you are reducing the bulk of the system. So these display systems can be compact. Holography is generating images using wave interference. So, theoretically, it's possible to achieve infinite resolution because it's a continuous wave, as opposed to existing ray-based displays, which are pixelated. And you can also generate, 3D within compact form factors, and you can move away from, moving mechanical or optical elements, variable focus displays that you've worked extensively on, so on and so forth.
Yeah. So if I follow correctly, then the form factor, resolution and brightness, plus you can do solid beam steering rather than using mechanical things, and so these are the primary benefits. There is one other question from the audience. Henry Fuchs is asking, can you say more about the human subjects, what they actually saw, and can you also elaborate a little bit more on simulated holograms?
Yeah, so the subject saw for a fixed field of view, which we maintained at 60 degrees. And this field of view got adjusted based on the emulated environment that the user is looking at, based on the monitor and stuff like that. And based on these parameters, the extent of foveation and the speckle noise will be automatically adjusted. And we evaluated for several images in a randomized control fashion. So it's a 2FC study where the subjects were shown images of random conditions and then evaluated for their score on, like, subjective or perceptual score on which image is better in an A/B comparison. Yeah.
I'm hoping that this is an answer to Henry's question. Maybe I can ask one last question before we conclude this session. In my knowledge, there are two types of speckles, objective and subjective speckles. If I understand correctly, your work is dealing mostly on subjective speckles. You need an understanding on the human eye itself to characterize these things correctly. But did you also look into, accounting for the objective parts, like actual things in your setup causing speckle because they are imperfect? Can you elaborate a little bit more on that front?
Right. So, yeah, exactly. There are two kinds of speckle, objective and subjective. And specifically in this work, because we wanted to evaluate the subjective speckle using a prototype display where, there is some amount of objective speckle, even just by the nature of using a laser source. That's a problem. And this objective speckle can arise from, nonlinearities in the SLM, dust that is scattering light, and the laser itself. So this basically means that for reducing the objective speckle, we need really well-calibrated systems and things, devices that are running close to ideal, or something that we can calibrate well. And the hardware in the loop techniques that I was talking about, those I think do a pretty good job in sort of compensating for these objective speckle or many aberrations in the real systems. But this definitely requires that we have devices that are really good. Yeah, especially SLMs that are really good.
Yeah. Thank you, Praneeth, for the nice presentation and also answering our questions. A huge applause to Nannan, Jingyu, Praneeth, Vanessa, and Mikhail for their nice presentations. This concludes our session. There will be a chat session in GatherTown to interact with the others after this session. The chat session will happen in track B rooms in the GatherTown. If you're curious to explore greater details of these works from our session, please plan on attending. And thank you very much for being here with us today. Thanks.